Thanks, Chirath. So today I'll be talking to you about securing Kubernetes. So in this session, I'll be talking about from a point of view of an attacker and how an attacker might try to sabotage a cluster and how we can prevent it. So as the first slide, I'm introducing you to the area of attack when it comes to a Kubernetes cluster. And at the bottom, you can see infrastructure as cloud, which is basically where you have your data centers, your firewalls, your network and servers. And on the next layer, we have our cluster where we have RBAC, authentication, authorization. Then we have admission control and we have network policies. On top of that, we have containers where we have container sandboxing, image restriction, privilege, escalation, supply chain, etc. And finally, we have developer discipline as the code base layer. So let's look at the first scenario. Attacker has access to your network. So now the attacker has somehow found a way to find your network, and now how can you prevent that? So basically, if you're using cloud, you can basically use SSH based key auth, and then you can make your Kubernetes API private to avoid these attackers or intruders discovering your API and try attacking it. And then you can have a firewall. You can secure your network through a firewall, and then you can have proper RBAC policies implemented in your cloud and also in your cluster. The next scenario is attacker has access to your Kubernetes control plane. So now the attacker has somehow gotten through your network, and now it has access to the infrastructure of your Kubernetes control plane. So before jumping into what we can do, let's just go through a few slides on how what Kubernetes RBAC is and what things are. So on the first slide, we have on the left we have who can access. So in Kubernetes we have two types: users and service accounts. Users are for humans, and users are someone with a cert and key, and the certificate is signed by the certificate authority of the cluster. Cert is managed by external to the Kubernetes, and it's not a resource in Kubernetes really. As I mentioned, it's handled externally. And then we have service accounts. So service accounts is for processors. It's not for human use, but rather when there's a pod or some other resource in Kubernetes trying to talk to the Kubernetes API, let that be a worker node, let that be a pod, CRD, whatever, they need a service account to access the API. So these are the users in a Kubernetes API. And then comes permission. So as you can see on the right hand side, we have two kinds of permissions. One in blue is called role, and the one in orange is called cluster role. So as you can see, the role is namespace bound. So when you create a role, it only affects a namespace, whereas when you create a cluster role, it's rather global in Kubernetes. It's accessed across all the namespaces in the cluster. And then to bind this role into a user or a service account, we have something called a role binding. So there are two kinds of role bindings, one being the name role binding itself, and the next one being the cluster role binding. So role binding is also namespace bound, and when you have a user, you can bind a role to that user in a given namespace, and that role can either be a role or a cluster role. But when it's a cluster role binding, it's more advanced, and it has a lot of privilege, because it doesn't scope into a namespace. It's there for the entire cluster. So when you do a cluster role binding to a certain person on a certain permission, the person can access that permission across all the namespaces in the Kubernetes cluster, which is a bit dangerous. So we'll look at an example in the next slide. Here we have John, who can do read secrets in the foo namespace, and there's a role called read secret role in foo namespace, and you can see on the slide that there's a read secret role binding to John, which gives John access to read secrets in the foo namespace. That is all right. Then there's Jane. So Jane needs access to read and write secrets to the foo namespace. However, read and write secret is a cluster role we have created for some reason, and in this scenario we can still create a role binding to the cluster role, which is read write secret to Jane, which gives her the correct access to full namespace. But now then look at the admin user. Admin user, we have given admin user read write secret cluster role binding, which means the admin user, as you can see from the red dotted lines, that they can read across namespaces of all the secrets that there are on the names, all the namespaces available in the cluster. So this can be pretty dangerous if you don't properly give access. So it's recommended that you use role bindings and roles instead of cluster role bindings. So hardening a Kubernetes cluster, we already spoke about RBAC policies and how to set it up. The next thing you gotta do is enable audit logging. So when a disaster or something has happened, someone has access to your cluster, your best friend would be logs. So you need to enable audit logging to figure out who did what on your cluster, so that you can trace what has happened and come to a conclusion. The next thing is you got to run CIS benchmarks on your cluster. This is mostly applicable for the clusters that you have done from scratch on your data centers, etc., because cloud managed clusters, GKE, AKS, EKS, these already have CIS benchmark reports on them. It's managed for you, but if you are managing your own clusters, if you are managing your control planes, run CIS benchmark and do the recommendations that they have given. The next one is, this is applicable for the clusters in cloud as well, managed clusters as well. Use a CIS hardened image. So by default, when you get a GKE or AKS or EKS cluster, they provide you a simple node, a node with a Linux runtime and containerd runtime for image for containers. But you can have CIS hardened node images which has more seccomp profiles, AppArmor profiles installed, baked deep within to the node image itself, which would give you more security. The next thing is encrypt etcd. Doesn't matter whatever the security tools you run, you might be running runtime security, sandbox, you might be running everything, but if your etcd is not encrypted in your control plane, any attacker who has access to your control plane should be able to easily look at the key value store that etcd provides and then read from it and get your secrets. Same goes for your secrets. So the common recommendation is, 12-factor apps taught us to inject variables as environment variables. That's not the case anymore. Now you have to mount them as files, right? So attaching environment variables can leak your credentials to someone who has access to the VM. So don't do that. Mount your variables as a file and then read from that file. Let's go to the next section. Attacker has access to a service account in your cluster. Alright, so now attacker has come in. Now it has the control plane access, and somehow it has access to talk into your Kubernetes API with some permissions, right? So how do we stop that? First of all, let's look at network policies. The concept of network policies is, as you can see on the example here, we have a web server in green, a Python backend and a database. And as you can see, there's no need for the web server to talk to the database. Only the Python backend needs to talk to the database, and on on a separate namespace we have something called a super important API. Right. By network policies, what allows us to do is we can specifically say which pod can talk to which service. Right. So we can specifically say web server cannot talk to the database, web server can only talk to the Python backend, and Python backend can talk to the database. So if somebody has exploited web server and has access to the web server, they won't be able to write directly to the database. They won't be able to access the database. And then if somebody goes and comes and gets into the Python backend, of course then they have access to the database, but still, because of network policies, they will still not be able to attack the super important API we have on a different namespace, right? So that's what network policies allow us to do. And by default, you have to use a CNI, a container networking interface plugin on Kubernetes that supports these network policies. Network policies can be at many layers. So commonly it's at TCP4, but layer 7 network policies supporting CNIs are there, such as Cilium, etc. So it's up to you to figure out which to use. Let's move into the next slide. So as I said, so for the first thing is you gotta use namespaces to isolate your tenants on the network. Then use network policies, which is the Kubernetes equivalent for firewalls. Then it's added advantage if you have an API gateway. You can even make the inter-service communication go through an API gateway. If you're using a service mesh, use MTLS. Or if you're using a service mesh that's powered by eBPF, network encryption, etc. happens by default. You can do that. So that's great. That means no one who has access to your infrastructure cannot overlook your network and figure out what's going on. Finally, there's something called admission controllers on Kubernetes. So there's open policy agent, Kivro, etc., which allows you to write policies on Kubernetes, your Kubernetes cluster, which I'll explain in a bit more in a later slide. So now, attacker has access to your code base. Now, if an attacker has access to your code base, attacker can do a lot of things. They can insert malware, they can insert vulnerabilities and exploit them later. They can do a lot. So to avoid this, you can do a few things. First one is, of course, static scanning. With your CI pipeline, you can do SonarQube scan, etc., and figure out if you are committing any sensitive information to Git, which is accessible by anyone if it's public. And then you can do code vulnerability scanning, as I mentioned. And then you have to keep scanning these. It doesn't matter, like today you scan it, it's all good, everything is green, but there could be an exploitation or a vulnerability discovered tomorrow. So you gotta scan on a daily routine or on whatever the preferred way that you do. Then goes image vulnerability scanning. So here our images might contain vulnerabilities. This also, again, you gotta scan at an interval or a duration. You can't just scan once and if it's okay, you can just forget about it, right? You gotta scan continuously. And exploiting a vulnerable image could lead to privilege escalation. Someone can get remote shell access. Your information could leak. Someone could give you a DDoS attack within the cluster. I personally use Claire, but people use Trivi and any other tool you can do to use image vulnerability scanning. And then there's another one called configuration scanning. So configuration scanning is when you're committing your YAMLs to your GitOps repository, etc. You can easily check them via Checkov or something else and see if you are missing anything, if you are missing a trick, if you are missing any configuration, security configuration or a policy. So it allows you to, it gives you feedback and you can fix them and secure your pipeline. So let's talk about Kubernetes admission controller, which I promised I'd talk in the previous slide. So let's see what it does. So in this scenario, there's a create pod request by a user. So when that request is gone to the Kubernetes API via kubectl, what happens is, firstly, it figures out who you are, right? Then it goes to the authorization. What can you do? Can you actually create a pod? Then finally, there's something called admission control. So in admission control, there are so many policies, even we can write our own policies. In this scenario, what it's going to look at is whether have had the pod limit has been reached on the given NS, whether you are able to create a pod or not. So admission control has two types. When we plug in, we have something called validating webhook and a mutating webhook. So validating webhook is a read-only type where it scans a given request and it just either allows it or denies it. This is perfect for third-party policy controllers like Open Policy Agent or something else. So here you can give any additional policies like don't pull images from public Docker, right? Pull images only from your private Docker registry. So you can give these policies and it would automatically deny at the admission control level when you give that policy via a third-party policy controller, or you can write your own validating webhook for it as well. Then there's mutating webhook. So that's a bit different. So it changes the payload dynamically. This is mostly used with CRDs and controllers that work with these operators that CRDs. So here you give a payload and according to some logic, it changes the payload dynamically and applies to Kubernetes in a different manner, right? So that's what Kubernetes admission controller does, and this would allow you to write your policies and secure your cluster. Right. The next step is now the attacker has access to your container. Somehow they have exploited your container. Now they have a shell. They have a shell access, and now let's see what we can do. So when it comes to container hardening, when you are building the container itself, there are some best practices that you got to follow. First thing is remove the bash shell, right? So that they won't be able to access your shell remotely. Make the file system read-only so that they won't be downloading anything or writing anything into your container file system. And then make sure the user is running as a non-root user. So when these are done, it's hard for us to, for an attacker to attack and exploit a container. So basically make your container immutable. Then there are other things that we can do. There are images which we don't have access to, to change the image, right? There are scenarios like we don't build the image, somebody else built it, we only run it. So in those scenarios, we can use Kubernetes without changing image to enforce immutability. So we can run there's this thing called startup probe in Kubernetes, where a container is running. You can run some script before the container actually starts running. Using that, we can remove bash if we want to, and we can set like run as group, run as user, run as non-root, set security context, remove privilege escalation. Can do a lot of things. So by using those, we should be able to make the containers immutable at a Kubernetes level as well. Then comes runtime security. Doing all of that is sometimes not enough, and you need more. So let's look at how containers work and what this runtime security means, right? So as you can see in a VM, when a container is running, it's running at LXC, on top of LXC, and then we have Linux kernel at the below, right? So basically a container is a group of namespaces and C groups. So when containers are making this doing things, it does syscalls to the Linux kernel. So say that means if there's a vulnerability in the Linux kernel, the container should be able to exploit it if someone with the proper knowledge and tools are there. So first thing to do is, as I mentioned earlier, disable privilege escalation and drop all the capabilities of a container, and then only add the things that are needed using Kubernetes constructs. And there are things like AppArm and seccomp profiles, which restricts the syscalls that you make to the Linux kernel, so that you don't make any weird ones and try to exploit our kernel. Then there's container sandboxing. There's Firecracker, there's gvisor. There are a few out there, which is makes this issue go away, but on top of it adds more performance issues. But still, it's great if you're running a multi-tenant system and if you don't trust the images. Then there are tools like Sysdig, Falco, etc., which monitors the anomalies of the container runtime and then gives you alerts like this is happening, stop this, etc. Right? So that's container runtime security for you. So you gotta conceal your information. This is something I told earlier as well. I asked you to do not inject environment variables, but rather do them as file mounts. And when you are doing that, it is recommended to inject via secret manager at runtime. Don't save it as secrets on Kubernetes itself. Base 64 is not an encryption. So use HashiCorp Vault or Azure KV, AWS Secret Manager, Google. There are so many secret managers out there. Use one of them and then inject your information, sensitive information, as files to the container at runtime. You can very easily do that with those technologies. And I already told, make your container root the system read only, and this is a developer discipline. Do not lock sensitive information. So comes to the final thoughts. Kubernetes security is still new, and vulnerabilities get discovered every day and then they get patched frequently. So update your clusters as soon as you could. If you're running your own or even in cloud, just keep upgrading your clusters. When it comes to managed Kubernetes clusters in the cloud, security is mostly, 70% of security, control plane security, it's managed. You don't have to do much there. And many organizations today need some level of multi-tenancy. They might have different teams, etc., working different projects and within a shared Kubernetes cluster. So these could be, these things that I told in this slide, in this session, would be appropriate if you can implement them in these scenarios. So keep the proper standards up and follow up, and things should be all right. That's it from me today. Thank you, and I hope you learned something today. Over to you, Chirag.